Hello, welcome. In this lecture, we will be discussing asymptotic notations. One of the performance measures of an algorithm is knowing how much time that the algorithm takes to complete. To find the time taken by an algorithm, we try to count the number of steps it takes to complete. But finding the exact number of steps is often difficult. Instead, we use asymptotic notations to understand how the time increases as the input becomes larger. Let us quickly recap what we had discussed in the previous classes. We have defined the efficiency of an algorithm is typically measured how much time that it takes to complete. That's what we said it as time complexity of an algorithm. How much space it takes to complete, that's what space complexity. So as we are expected to specify the time complexity or a space complexity of an algorithm without actually executing on a machine. So we need a machine independent way of specifying and especially focusing on how it scales for a larger values of n. So that is where we are going to use asymptotic notations. If we have to actually measure the performance by running, then it depends on many other factors like what is the hardware, what are the compiler optimizations, what programming language. So here we need a way which is a mission independent way, and how especially focusing on how it grows for large values of n or large values of input sizes. Okay, so let us try to understand the definitions. The first notation is the BigOh notation. So here we have two functions, f of n and g of n. A function f of n is BigOh of g of n if and only if there exists a positive constant c and n naught such that f of n is less than or equal to c into g of n for all n greater than or equal to n naught. So f of n is the running time of an algorithm, and g of n is a simpler function that is generally used to specify as an upper bound. So f of n is less than or equal to c into g of n. So it acts as an upper bound, and generally it is used to specify the worst case scenario, the maximum time that the algorithm takes. So let us try to understand with an example. Suppose you have f of n as 5n plus 3. Now 5n plus 3 can be written as some less than or equal to some c into n for n greater than or equal to n naught. If we choose c as 8, 5n plus 3 is always less than or equal to 8 into n for all values n greater than or equal to 1. So we can say that 5n plus 3 as BigOh of n. Similarly, 2n square plus 10n plus 100 also less than or equal to some c into n square. If we choose c as 112, so this always less than or equal to 112 n square for all n greater than or equal to 1. So we can say that 2n square plus 10n plus 100 is BigOh of n square. That means this is like we are classifying the growth of a function. Either it is a 5n plus 3 or 10n plus 9 or 50n or 100n, all will be classified as BigOh of n. Similarly, 2n square plus 10n plus 100 or 100n square plus 50n, all those will be classified as BigOh of n square. So let us try to understand the second definition, that is BigOh notation. A function f of n is omega of g of n if there exists a positive constant c of n naught such that f of n is greater than or equal to c into g of n. So Now g of n acts as a lower bound to the f of n. This is generally used to specify the best case scenario. What is the minimum time that the algorithm takes? So now 5n plus 3 5n plus 3 is greater than or equal to some c into n. If you choose c as 4, 5n plus 3 is always greater than or equal to 4 into n for all n greater than or equal to 1. So we can say 5n plus 3 as big omega of n. Similarly, 2n square plus 10n plus 100 is greater than or equal to some c into n square. Some 2, if we choose c as 2, so 2 into n square for all n greater than or equal to 1. So we can say that 2n square plus 10n plus 100 as BigOh of big omega of n square. Okay, so let us try to understand the third definition, that is theta notation. So a function f of n is theta n if and only if there is a positive constants c1, c2 and n0. So now here g of n acts as a both lower bound as well as an upper bound, that is a tighter bound. So if f of n is BigOh of g of n as well as big omega of g of n, then it is theta of g of n. So f of n grows at the same rate as g of n. That is what theta of n. So let us try to understand an example. Now as we had seen from the previous examples, 5n plus 3 is both BigOh of n as well as big omega of n. We can say that 5n plus 3 as theta of n. Similarly, 2n square plus 10n plus 100. From the previous examples, it is both BigOh of n as well as omega of n. We can say it as both BigOh of n square as well as omega of n square. So we can say it as theta of n square. Okay, so now we'll try to do one more example. Suppose this is a common thing that you get for all the sorting algorithms, where you get first n comparison, next n minus 1 comparisons, next n minus 2, so on, plus 1. That is the case for n into n minus 1 by 2 for sum of n natural numbers. So we will get n into n minus 1 by 2. So in that case, so as we can see that n into n minus 1, 2 is BigOh of n square, because n square by 2 minus n by 2 is less than or equal to half into n square. So if I choose half as c, so half into n square is always greater than half into n square minus n by 2, because there is a subtraction term here. So we can say that as BigOh of n square. Now, which can also be said as big omega of n square. So if we have n square by 2 minus n by 2, so here we are subtracting n by 2, but if we subtract a bigger term than n by 2, then n square by 2 minus n by 2 is greater than or equal to that term. So let us suppose if we subtract n square by 4, so then we'll get n square by 2 minus n square by 4. So this is less than this n into n minus 1 by 2. So now from this we can say this as n square by 2 minus n square by 4 as n square by 4. So this will be 1 by 4 into n square. So now we have some constant into n square, which is less than n into n minus 1 by 2, and this is true for all n values greater than 2. Okay. So we can say that the same function n into n minus 1 by 2 is both c1 into less than c1 into n square and greater than C2 into n square. So we can say it as theta of n square. Okay. Now, so let us consider example. Suppose you have this code snippet and you have to find the time complexity. Then we can see that the statement inside this nested loop will be executed n into n times, that is, we can say it as theta of n square. Similarly, if you have two for loops, one followed by another, the first for loop takes n times and the second for loop takes m times, then the time complexity is n plus m. The function is n plus m. Suppose if we know that m is some proportional to n, something like m is equal to 2n, then we can say that this as theta of n. But if m and n are independent, then it can be denoted by using a BigOh of n plus m. Okay, and the homework problems is we find the maximum element in an unsorted array of size n. Use the notations BigOh, BigOmega and Theta to find the number of comparisons. Similarly, prove that 5n square minus 6n as theta of n square. Similarly, sigma I is equal to 0 to n, I cube as theta of n for 4. Similarly, is 2 power n plus 5 is same as BigOh of n, BigOh of 2 power n. Now these asymptotic notations are helpful in understanding how the time increases as the input becomes larger, and BigOh is used for specifying the upper bound and BigOmega is used for specifying the lower bound. Theta is for specifying the tighter bound, and which can use it for comparing the efficiency of two algorithms.